Hello, Pre-Calc. You're watching this after Tuesday's class, 418. We're back and the end line is in sight. So let's continue our study of probability, and I'm going to define for you a term that we need to know, and that is mutually exclusive. Two events are mutually exclusive if they have no outcomes in common. So if you have two events are mutually exclusive if they have no outcomes in common. For example, if you're rolling a die and the event of getting a 3, so we'll say the event is rolling a 3. And we'll call that event A. And event B is rolling a 6. So these two events do not have any common outcomes. They are mutually exclusive. When you roll a 3, you can't roll a 6 also. So these never overlap. The event rolling a 3 and the event rolling a 6 are said to be mutually exclusive. Suppose we toss a coin. The event is heads, and the other event, event B, is tails. These are said to be mutually exclusive. When you toss, if the event is described as being heads, then it cannot also be tails. These are mutually exclusive. So, since we're in our discussion on probability, the probabilities say A and B are mutually exclusive. So what is the probability of A and B happening at the same time? Another way we can write that in probability or in math language is A intersect B. This upside down U is read intersect. It means and. So what's the probability of A and B happening? In these mutually exclusive examples, you can see the probability of tossing a coin and obtaining a head and also a tail at the same time is 0. It's not possible. And that's true for any two mutually exclusive events. So, all right, what then is the probability when you roll a die? What's the probability of rolling a 3 and a 4? The probability is 0. So what's the probability when you toss a coin? Probability of getting heads and, oops, it's supposed to be curved, U, upside down U like. Probability of getting a heads and a tails is 0. And there are lots of other examples. What's the probability of winning and losing a game at the same time? Those do not overlap. If you win, you have not lost. If you lost, you have not won. So the probability of winning and losing at the same time is 0. All right, so that is when the word connecting the events is and. Let's stretch a little bit. Stretch those stiff mathematical muscles and do the probability of A or B. And let's say these events are mutually exclusive. So this time, if A and B are mutually exclusive, so they don't have any outcomes that overlap or are in common, so if you have an event, if event A is defined, it will not include B. If event B has been defined, it will not include A. So they're mutually exclusive. So what's the probability of A or B for mutually exclusive events? It's going to be the probability of A added to the probability of B. So what's the probability when you flip a coin? What's the probability of getting an A or getting a head or a tails? Head or tails? Well, the probability of head or tails is going to follow this pattern. It's going to be the probability of heads plus the probability of tails. And that will equal 1/2 plus 1/2, which equals 1. So it's a certainty. When you flip a coin, you're either going to get head or tails. So the probability of 1 means it is certain to happen. We read this value, or there's another way of writing this OR idea, and that is this symbol. And that is red union. And sometimes we just read it OR, that's what it means. A union B is OR. So, let's draw the line, and this time let's look at A and B not mutually exclusive. Alright, so we've talked about a lot of examples for ones that are mutually exclusive, but let's look at two events that aren't mutually exclusive. So that means they have some sort of events in common. So part of their outcomes they share. So I can best show you with a Venn diagram. And let's say I have a group of people, and these in this set are red-headed. So there's 6. One, two, three, four, 6. 1, 2, 3, 4, 5, 6, 7. I mean, not 6. All right. But these two also shared common outcomes with the group boys. So we have redheads and boys, and there's 1, 2, 3, 4, 5, 6 boys total. And then out here we've got 1, 2, 3, 4, 5 outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 outside. Alright, I think I have it set up the way I want it. So copy this Venn diagram. So the group in here are all red-headed. So the group here are boys. So their intersection is red-headed boys. Do you see how the two sets share common outcomes? And these in here are red-headed girls. These out here are boys that are not red-headed. And what are these? Well, they're not redheads and they're not boys, so these are girls that are non-redheads. So every person has their spot in this Venn diagram. This particular group has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 people that have been categorized in this Venn diagram. Alright, I don't want to go over 15 minutes on this part, so I'm going to shut down now and open up on part 2.